In this video, we'll be looking at the reduction formula. We'll be looking at how we can systematically reduce integration involving higher powers of the function. So this topic is mostly treated in further pure mathematics. So this is a question. Given that I, m is the integral from 1 to e x raised to the power m ln x raised to the power n dx, m and n are non-negative integers. Show that m plus 1 multiplied by m, n is equals to e raised to the power m plus 1 minus n n minus 1, where m is greater or equals to 0, n greater or equals to 1. So they're essentially asking us to show that the reduction formula for this integration is equal to this equation. And let us use this reduction formula and further evaluate and find the value of this integral. Now, one important skill that you need to know here is integration by part, because integration by part is a technique which is used to integrate the product of two functions where one is not the derivative of the other by also systematically reducing its power. And integration by part states that the integral of u dv by dx is equal to uv minus the integral of v du by dx. What does that mean? It means when you want to apply integration by part, you need to let one of those functions, u, which you will differentiate to obtain du by dx, and the other function will be let dv by dx, which you will integrate that function to obtain v. Now, let us take the question and answer. So this is m, n to be this integral. And I know most of you will quickly let u to be x to the power m and differentiate to obtain du by dx. But this is not the right way to do it, because if you are differentiating u and you want to integrate ln x, then it will be more complex, because integrating ln x on its own, you need to apply integration by part. So rather, I will let u to be ln x raised to the power n, and I will let the v by dx to be equals to x raised to the power m. Now, let me look for du by dx by differentiating this function. I can apply the chain rule to differentiate this, because this is function of a function. How do I apply the chain rule here? I bring down the power, I maintain the function, I subtract 1 from the power, and I multiply by the derivative of the function. So bringing down the power n, I will have m. I maintain the function ln x, raised to the power, I subtract 1 from the power, I have n minus 1, multiplied by the derivative of ln x, which is 1 on x. Now, integrating x raised to the power m is rather straightforward, because I will just add 1 to the power and divide by that new power. So I'll be having 1 divided by m plus 1 x raised to the power m plus 1. Now that I have all the components needed to apply integration by parts, let me go ahead and apply it. So the m, n will be equal to uv. I multiply the function u by the function v. Multiplying these functions, I get this, minus the integral of v du by dx, and multiply these functions. So I'll multiply this constant term to obtain m divided by m plus 1. Then I take this function and multiply, so I'll have x raised to the power n plus 1 times ln x raised to the power n minus 1 divided by x. So at this juncture, I'll need to bring the terms in x together. And the power of x is 1. So if I apply the law of indices to this x and it reciprocates, I will now have x raised to the power negative 1, which add up to this 1 and gives x to the power 0. So the x vanishes, and I will be left just with x raised to the power m. So this is what I have: n divided by m plus 1, x raised to the power m, ln x raised to the power n minus 1 with respect to x. So I can bring out this constant, then n divided by m plus 1 goes out of the integral sign, and I maintain everything else. Now, at this point, Oh, I've forgotten the limit. So the limit here is from 1 to e. I have to plug the limit everywhere. Now notice that 1 divided by n plus 1 is common to these terms. So in order to eliminate or cancel out this denominator, I can multiply each term by n plus 1. Doing the multiplication, I get n plus 1 into im comma n is equals to n plus 1 cancels out from this first term and cancels out from the second term, and this is what I have. So at this juncture, I can plug in the limits. So plugging in the limits I'll plug in the upper limit, which is e, into this function, and I subtract the lower limit. So plugging in e, I'll be having e raised to the power m plus 1, ln e raised to the power n, and ln e is 1. 1 raised to the power n gives us 1. So I'll just be left with e raised to the power n plus 1 as the first term. Now, when I plug in 1 into the function, ln 1 is 0, so the whole term boils down to 0 and vanishes. So I'll just be left with minus n. Now, let's compare the initial integral that was given to us and what we have now. Notice that they are the same, only that the exponent of m, the exponent of n is subtracting 1. So I can now write it as n multiplied by im comma n minus 1. That means the power of ln x has been reduced by 1. So this is what we were asked to prove, and we have arrived at it. I hope you have understood how the steps we have taken to arrive at this proof. Now, I can simplify further by making im comma n the subject by dividing both sides by n plus 1. So I get this, where im comma n is equal to the initial integral that was given to me. This is the integral that asked me to solve. The integral from 1 to e x squared ln x raised to the power 3 dx. Now, looking at it keenly, you notice that the power of x is 2, so m is equals to 2, and the power of ln x is 3, so n is equals to 3. Now, applying the reduction formula to integrate, I'll now be looking for I2, 3, which is equals to, I'll substitute m with 2 and n 3 into the reduction formula. So that gives me e cubed minus 3 I2, 2, because 3 minus 1 gives 2, divided by m plus 1, which is 3. Now, at this point, I can separate the numerator, and I'll be having 1/3 e cubed minus 3 cancel out with this 3. I have I2, 2. Now I can apply the reduction formula once more. This is a reduction formula, so I'll plug this into this reduction formula. I'll keep 1/3 e cubed as is, minus I2, 2. So I plug in m as 2 and n as 2 into the reduction formula. So we're having e2 plus 1 is cubed, so e cubed minus 2 I2, 2 minus 1 gives 1. Notice that the power of n is reducing, is systematically being reduced, divided by 3. Separating the numerator again, I'll be having negative 1/3 e cubed, then positive 2/3 I2, 1. So at this point, these are like terms. They can cancel out because 1/3 e cubed minus 1/3 e cubed gives me 0. So I'm left just with 2/3 I2, 1. And here m is 2 and n is 1. So I will apply the reduction formula once more, because the validity of m and n is that m is greater or equals to 0 from the question, and n is greater or equals to 1. So I can apply reduction formula to m to n just one more time. So applying it this time around, I'll have 2/3. I apply it, I come back here, m is 2, so e cubed minus n is 1, 1 times I, m is 2, then n was 1, 1 minus 1 gives me 0, divided by 3. So let me separate the numerator again. I have 2, 3 times 3 gives 9, so I have 2/9 e cubed minus 2 over 9 I2 comma 0. At this point, I can no longer apply the reduction formula because n has to be greater or equals to 1, but n here is 0. So instead, I will just plug it into the initial integral and integrate it. So I'll be having, let's recall that Im comma n is equal to the integral from 1 to e of x to the power n ln x to the power n. So how do I express I2 comma 0? So I2 comma 0 means I'll replace m with 2 and then of course n with 0. So this is supposed to be 0. And so ln x raised to the power 0 gives us 1. So I'm left just with x squared. And this is very easy to integrate. In fact, this is a piece of cake because integrating x squared just means you add 1 to the power and divide by the new power. So I'll be having x cubed divided by 3. So at this point, I'll plug in the limits so that I can simplify it further. So I'll just have 2 over 9 e cubed minus 2 over 9. Then I plug in e. I have e cubed on 3 minus 1/3. Then multiplying out the bracket or distributing negative 2 over 9 into these terms, I'll obtain negative 2 over 27 e cubed, then positive 2 over 27. These are like terms because they are terms in e cubed. I just add their coefficients. So I'll be having 2 over 9 minus 2 over 27. That gives me 4 over 27 e cubed, then plus 27. Then at this point, I cannot simplify further. Or what I can do is just to find the LCM. And of course, their bottom are the same. I maintain 27 and just add their numerator. And now the result, which is I2 comma 3 is equals to 4 e cubed plus 2 divided by 27. And I've come to the result of that integral. I've integrated it by applying the reduction formula. I hope you have understood the steps I follow to arrive at the answer. But if you do have any questions, then leave it below in the comment section. Then I will do well to answer them. And if you have any appreciations or criticisms or corrections, do well to also allow them in the comment section. I will really appreciate them. Thank you so much for your time and your patience, and I will see you next time.